In the morning, I presented like our low-level communication infrastructure, but especially on the training and inference, there are a lot of challenges in the upper layer also. Like how do you really keep the communication computation busy? So we have two papers. One paper, Lang will present, which is characterizing communication patterns in distributed large language model inference. This is actually accepted in the Hot Eye. He will formally present at Hot Eye, Hot Interconnect on Thursday. And the other paper will be presented by Jingan on training ultra-long context language model with fully pipeline distributed transformer. So this was presented, I think, 2 months back at MLCs. So while we are working the MIPitch and high TM on the lower layer, we are also working on the upper layers, like the really optimizing all this training and inference. So these will be short talks. So I think let's get connected and keep moving. Choose to mirror, it says. Okay. You want to use this or this or this? No.
Hello. Okay. So, hey everyone, I'm Lane, and I'm currently an upcoming fourth-year PhD student. My mentor is Dr. Panda. Apparently, I work in our HiDL project in our Now lab, and today I'm going to share some preliminary results that we find when we are trying to characterize the communication patterns in large-scale distributed model inference. So we'll start from 4 parts. We'll start from introduction and motivation. So as we all know, inference now is the hot topic. Several years back, pre-training is the hot topic, but right now, given the rise of more reasoning capabilities, decision-making, coding capabilities, and upcoming new novel techniques for reinforcement learning, scaling inference time compute is pretty the hot topic right now. So the inference is technically the process of using a pre-trained language model to generate text or predict on a given input. So basically, it's just forward pass, no backward pass, which is in pre-training. So there's some unique techniques or characteristics in large language model inference. Similar to pre-training, inference has several challenges. We need to deploy the model on multiple GPUs, multiple hosts, multiple nodes, and there's definitely communication overhead. We have to pay the cost. And there's also unique communication pattern. This pre-fill decode stage disaggregation, which is for prefill, it is compute bound, where you process a full batch of the prompts, and with decode, you spit out tokens after tokens, which is memory bound. Some key metrics to determine whether your inference workload is efficient or not include server level objectives, latency, time to first token, TTFT, time per output token, TPOT. So let's look at some problem statements that we are trying to cover here. So what are the predominant types, volumes, and patterns given a framework that we choose? What are the type of communication during multi-GPU inferencing? Can we develop some analytical models to predict such communications with certain parameters like parallelism degree, the layout, the model architecture, and such? And what is actually the impact of communication patterns of the volumes when it comes to SLOs? And also we analyze some SLOs under different type of parallelism layout. As you may know, we can specify different TP or PP degree when you're inferencing a model. So if we look at the trying to develop an analytical model, we try to focus down into several variables. We have hidden dimensions, number of layers, the bytes per element, the prefill sequence length, which is the length of the prompt that you fill, that you push to the prefill stage, the number of attention heads, tensor parallel size, which is the degree of tensor parallel, pipeline parallel size, vocabulary size, decode sequence length, which is the total number of tokens that you need to spit out during decode stage, and head dimensions. So in this talk, we'll cover about tensor, pipeline, and hybrid parallelisms. And we focus on VLM framework, and currently we focus only on dense transformers. And we also focus on Llama style type of architecture in this talk. So if we look at tensor parallelism, it is a well-known technique proposed in Megatron library. So on the right-hand side, you can see the figure that we have two RDUs for the MLP for the attention output projection, and the two RDUs for MLP down projection. This includes the backward pass. So for inference, for each layer, we only have, for each transformer block, we have a total of two RDUs and a message size of H, which is the hidden dimension of the elements. So before everything got passed to the transformer block, we have a one RDUs at the embedding layer per token, and a final one gather at the final logic computations per generated token. So if we look at the total volume of tensor parallelism, we will incorporate two calls of RDUs per layer and one embedding RDUs, and that's for actually how many, that's actually for all this prefill and decode sequences, and also apply additional bus bandwidth correction factor proposed by the nickel tests, and also at last we will depend on the gather volume. This is a pretty huge communication volume if you look at the formula. So if you look at pipeline parallelism, the main insights we have here, it is rather a lot less communication overhead compared to tensor parallelisms, because the only communication happening in pipeline is that we have to send the activations between pipeline links, so which is the P-1, which is the number of links, and the first pipeline rank received no input, the last pipeline rank produced no intermediate output. So this is for decode stage, we have just spinning one token by one, so it is only 2 times the hidden dimensions times the bytes per element message sizes. This is rather pretty less heavier than tensor parallelism. So if we look at multi-node deployment, we look at hybrid parallelism. We're trying to combine tensor and pipeline parallelism. So I'm going to focus here is that there's some difference in communications that happens at hybrid settings. So there will be an additional all gather to redistribute the activations among tensor parallel workers. So what this means is that when you pass activations from one pipeline stage to another pipeline stage, it will need a rematerializations of the previous activation sent from the previous tensor group. So before the activations are reaching out to the next tensor parallel group, you need to rematerialize the matrix using the all gather operations. A benefit of this is that the reduced volume will be reduced by P, which is the number of pipeline stages, and there will be a lot less reduced volume incurred in this hybrid layout. But additionally, we have all gather and all gather added to this formula. So the total volume of the communication will be all reduce plus all gather and point to point. If we look at some performance results, so experimental setup we have on the OSC Cardinal system, which is 4 H100s per node. We have NVLink within the node, and we have 4 NICs per node across the node, 2 for the infinite band connection across the node. We have PyTorch 2.6. We turn off torch.compile, no custom reduce, VLM V0 engine, nickel communication groups, and we test on 3 different model scales, 3 billion, 8 billion, and 13 billion. This is a single request batch size of 1 characterizations. I know there's a lot of attention is raised to multiple requests, but we want to make sure that the picture is clear here. So using single request, no batch size, no overlap at all. We collect our metrics using PyTorch profiler and VLM RESTful observability APIs. So we're gonna, running out of time, we're gonna go through some key takeaways. So basically, for tensor parallelisms, the reduced frequency and the message sizes, it depends on the number of transmortal layers and the decoding steps. The message sizes also depends on the sequence length and the hidden dimensions. So basically, larger model, larger reduced message sizes, more reduced. If we look at pipeline parallelism, it is kind of a moderate message sizes with really high frequency, because with a number of links for each token, you have to do a communication. Decode stage is more communication heavy, and for pipeline and tensor parallelism, reduce and point-to-points are the major operations when we only consider these 2 parallelisms. So if you look at the volume, if we're taking hybrid, if we look at different models, different sizes of models, we can see that the hybrid parallelism strikes a balance between the most communication heavy tensor parallelism layout and also the minimal communication layout PP, which is pipeline parallelisms. So some notes on this is that tensor parallelism definitely has the most communication overhead, but pipeline parallelism has the minimal pressure on network, but also it is detrimental to latency, because for single request, single batch size, you are underutilizing the GPU compute, you are creating a data dependency between the links. So if we look at the SLOs for tensor parallelisms, we focus on time to first token, which is the prime indicator of the prefill stage. And if we look at TPOD, which is time per output token, which is a prime indicator of the decode stage. So time to first per token is primarily compute bound. If we split the computations among more GPUs, it is going to decrease the overall time. As we have for next per node for internode, the speed that we gain from splitting the computations, it is overcoming the internode communications in this case. If we look at time per output tokens, which is reflective of our decode stage, which is more memory bound, TP8 will cross more internode boundary because we're initially initiating more communications across the nodes. If we look at pipeline parallelisms, which is also splitting the computations, but actually it is introducing actual data dependencies for single request workloads. So as we can see, if we create more links, more dependencies for cross nodes, eventually we'll hit the node boundaries. The time to first token will increase really dramatically. And if we go for the time per output token, which is when you go for the TPOD, where PP2 and PP4, they are still remaining very low because they are doing the links within the node using NVLink. And if we instantly cross the node boundaries, it is creating a huge pressure on the metrics. So if we look at the performance analysis for hybrid parallelisms, some key takeaways that we look at the metrics here is that we want to maximize the TP ranks during the prefill stage, because that will makes us have more competitive time to first token. And if we look at subsequently memory bound time per output token stage, we want to minimize the links, minimize the pipeline links. We want to make sure that it doesn't cross the node boundaries. And some some key takeaway here is that for pure tensor parallelisms, we has the best latency time to first token and teapot, which keeps the GPU busy. And also, given the advantage that we have 4 nicks per node and internode, links is relatively high in bandwidth. So the advantage of splitting the computations is overcoming the actual communication pressure here. So the worst case here is TP equals 4, PP equals 2. This is mainly because it is actually incurring a lot of TP collectives compared to more PP links. There's more communication here. And also the only data dependency link is across the node. So we'll come to some conclusions. We have decode stage dominates the communication frequency. We have R-reduce and point-to-point as the major indicator of communication here. Tensor parallelism has a better GPU utilizations as it scales pretty well, and but it also has a lot of communication overhead. So we want to restrict it into a node, but it also depends on the real deployment scenarios. Pipeline parallelisms have minimal communication overhead. It is suitable for low bandwidth environments and long generation tasks. While computation parallelizations can overcome communication overhead for short sequences, given some node configurations, it diminishes with longer sequences and internode deployments. So this paper is now on archive, and I will also give a more detailed presentations on Hautai this Thursday, and we welcome everyone to register for that, and we'll present online.
So we'll move to the second talk as we are running tight on the schedule. So Jingan, please proceed.
Ended before 5.
Running late. Yeah. 4:50, so just 10 minutes. Yeah.
Hi everyone. So I'm gonna go really quick with this. So this was a work in collaboration with Microsoft DeepSpeed team, and it was performed early last year and early this year. So this work was also presented in this year's MLSys conference. So the topic here is basically we're trying to do something for long context training, because right now people face some issues when you're trying to really train your large language models on long context. So this is the background. So before, like, we were comfortable with only 512 tokens, but now we're going to like 2 million or maybe 10 million tokens. So how are you gonna effectively train this long context on your hardware? So this is a table from the Llama 3.1 white paper. What you see here is basically when they go from sequence length of 8K to 128K, they are sacrificing a lot of GPUs from data parallel to context parallel, because your sequence is getting really, really long. So more GPUs need to be added into your context parallel group. And also you'll see a drop in the last column, which is the MFU, like how efficiently you're utilizing your GPU, because context parallel introduces a lot of communication. So that means there will potentially be a lot of idling time for your hardware. So why training long context really hard? So these are like some model training related knowledge here. So in model training, there are 4 parts. The first 3 parts has nothing to do with the context length of the model. So it only relates to like how large your model is. But as you increase the length of your, the input data, you will see that the activations are like directly related to the context length, which means that the tensor down there, it will get larger and larger as you increase the sequence size, the sequence length. So there is another very interesting feature of this training process is that if you look at the table on the right, these are the memory spikes, or we see the temporary memories required for every operation. So you will see that some operation requires you to allocate a lot of temporary buffers, and some requires less. For example, all-to-all operations here, because we're communicating Q, K, and V, and if you do it in a non-blocking way, that means you have to allocate the temporary buffer for on the receiver side, because all-to-all cannot be performed in place. So if it's not blocking way, then it's basically one extra memory. The biggest bottleneck comes from the backward of attention. That is where you need to allocate 8 ND, so 8 times more of temporary buffers in order to run the single operation. So these are the reasons why training long context is hard, because your GPU will basically get out of memory errors as you keep increasing the length of the sequence. So our intuition is very simple. So if you have a very long sequence, at a given period of time, your tensor cores is only capable of processing a part of the sequence. So during that piece of time, the rest of the sequence can just go somewhere else instead of reside on the GPU memory. So that is the central idea. It's very intuitive. So I will just first present our results. So compared to the previous state of the art, we are, on 4 A100 GPUs, you can train 2 million sequence lengths on a 7 billion model, which is 16 times longer than the previous sort used in the industry. And also we achieve 95% of theoretical T-flops, or like MFUs you can achieve. Okay, how many times? Okay, cool. So methodology part, we have 3 things here, but I will just put the first and second thing together. So trunking and offloading. So the idea again is very intuitive. So on the input part, you will see that if your sequence is really, really long, that means the S is very large, right? So what we do is because if S is so large, then the temporary buffers will get also very, very large. So what we can do here is basically we slice the input data into multiple chunks, and each time we only process one chunk. And this way we can control the size of the intermediate buffers. And we have to make sure all the following operations are also performed in that chunk. Then this basically means we have to rewrite the entire transformer code in the PyTorch code base, because every operation needs to be performed in chunk-wise. So this is the full pipeline here. So for every trunk, we do some operations in the middle. So it's on another GPU, which means there are some all-to-all operations performed, and then we do the attention updates, and we're offloading or we cache some of the trunks to the host memory while we're processing the current trunk. So it's like full pipeline kind of things. And this contains the entire, every single operation in the transformer layer, from your attention, from the rope embedding, from your FFN, and all the communication. And at the end, you have the gradient, back propagation, and that is also included. So we rewrote the entire pipeline of the transformers in PyTorch. Good. And the final part is called double buffer. So if we're talking about you're trying to offloading something, then for sure you are going to wait for the data to be prefetched, right? That will introduce some latency. But the thing here is that we did something here, we call it as zero latency. This is because we found that when you train the transformers, as the sequence length gets longer, the computation complexity in attention is O(n) squared. And the data loading is always O(n). So that gives us a hint that at some point, these two latency will match. And that is this point where we can hide the latency of data fetching by the latency of attention computation. So this gives you a more straightforward explanation. So attention increases by O(n) squared. Loading increases by O(n). So all we need to do is we find this proper sequence length or trunk size that the two latencies overlap with each other, and this is the point where the latency can be overlapped. Yeah, so in our practice, we basically found we tried different models, and we identified that 64K is the trunk size where our PCIe throughput matches the throughput of the attention computation. But of course, this will differ based on what kind of hardware you're using, like different version of PCIe, or you have more powerful tensor cores, etc. So this is the entire pipeline. We have different CUDA streams here. As we said, we modify the entire PyTorch code for transformers, so it's gonna get really complicated right now. But the code is open sourced in the DeepSpeed repo, so you can just go there and train, and we have tutorials there. Yeah, so these are like some profilings. Basically, we vary the trunk size, and we say the T-flops, which is how efficiently you're using your hardware. And the green line denotes the required HBM memory. So as you have larger trunk size, yes, you will see a very good T-flops, but you are also increasing a lot of intermediate, requirements for the buffer. So you'll find a point that, basically it's like a trade-off. And this is also very interesting. So this is the actual PyTorch profiling results during training. So as you can see that when you have more and more trunks, the memory spikes gets lower and lower. So there will still be memory spikes, but they all get slower. Again, this is like a very small model, so you won't see a big difference here. But on the biggest model, like 70 billion model, Llama model, we see that it's a huge difference when you increase more chunks. And this is the overall path. Again, so we do not start from scratch. We stand upon the previous giant's shoulders. So these are all the currently used training techniques that help us go to these very amazing results. So this is on one DGX node and train an 8 billion Llama 3 model. With our method is called FPDT, by the way. So the last column of the training strategies, where you can see that we support at the maximum of 4 million context size, and we are getting the highest MFU, which means that we used our hardware most efficiently. Yeah, I think that will conclude the talk. Again, the code is open sourced on the DeepSpeed repo, and you are welcome to use. Thank you.
Okay, so let's give thanks to both of them. I think if there are any questions, I think might be the banquet time and all. Please feel free to talk to Jengan and Lang, both of them there. So we have a tight day today. We have just kept a little bit of time for open mic. If anybody would like to talk anything, give feedback. Yesterday